I'd like to welcome you to the first of 5 webinars in our Anaerobic Digestion webinar series, Emerging Technologies to Improve Environmental and Economic Impact. This series is hosted by the Center for Sustaining Agriculture and Natural Resources at Washington State University in partnership with the Water Environment Research Foundation and the American Biogas Council. Funding for this series was provided in part by the USDA National Institute of Food and Agriculture and the Environmental Protection Agency. As I mentioned before, my name is Sonia Hall and I will be moderating this webinar. Before we get started, I'd like to just go over a few housekeeping items. First of all, in general, the webinars work best on your computer if you close out of all other applications. All participants will remain muted throughout the presentation. We will be having a question and answer session, and so there is a questions pod in your control panel. Please write in your questions at any time during the presentation in that pod, and we will read them out at the end. If you don't see the questions pod, there should be a little orange arrow that will expand or hide the control panel. There is also a screen button that will toggle to full screen, and you can switch back and forth between the full screen and the questions pod as you need through the presentation. If you do continue to have technical issues, please use the question pod, and we will do what we can to help you resolve them. Though, as I said, this has been a problem with GoToWebinar, and so we may not be able to solve it on our end, but we'll do everything we can. This webinar is being recorded, and it will be available for viewing freely on the CSANR website, and we'll give you the link to that here in just a few slides. And finally, at the end of the presentation, there will be a brief evaluation survey. If you could take a few minutes to just fill that out, we'd much appreciate it, as that is very helpful to us in improving webinars that we offer. I would like to now introduce our webinar co-hosts, who will briefly share their perspective on this webinar series. First of all, I'd like to introduce Barbara Schwartz. She's the Multimedia Production Director with the Water Environment Research Foundation. Barbara, go ahead. Oh, hang on, I'm not. Now, yes, Barbara, go ahead, please.
Good morning. The Water Environment Research Foundation is an independent scientific research organization that focuses on our water resources. WRF operates with funding from subscribers and grants from the federal government. WRF represents a wide spectrum of the water sector and stresses collaboration among teams of water resource professionals. With funding from a U.S. EPA STAR grant, WRF established the National Research Center for Resource Recovery and Nutrient Management. The center's goal is to provide innovative data, demonstrations, and tools to use valuable resources in waste such as food and manure to form an integral part of a sustainable managed system that includes the nutrients, energy, and water. Anaerobic digestion and the enhancement process to generate renewable resources such as biogas for energy recovery from our waste is a major focus of WRF's energy research program. As part of this focus, WRF's National Research Center for Resource Recovery is sponsoring research at Washington State University to integrate nutrient recovery and anaerobic digestion advances. Our goal for these web seminars is to help share information about the important advances in the technology. Thank you.
Thank you, Barbara. I'd now like to introduce Caroline Peet, Project Assistant with the American Biogas Council. Caroline, go ahead.
Hello, everyone. The American Biogas Council is thrilled to be a partner with WSU and our co-partners to put on this webinar series. Across the biogas industry, as our members try to develop new biogas systems in nearly every corner, we see a lack of education and awareness about the great things biogas systems can provide all of us, economically and environmentally. Collectively, we have a lot of work to do to raise awareness of what biogas systems can do to create nonstop, reliable, 24/7 renewable electricity, heat and fuels, and create nutrient-rich soil amendments, while also providing systems that allow us to manage organic materials, which make up about 1/3 of our garbage, as much as glass, metal, paper, and plastics combined, and also allow us to recycle nutrients so we don't have to import phosphorus or fossil fuels to make nitrogen for the fertilizers that our agriculture industry needs. The more people that understand these basic benefits and the multitude of secondary and tertiary benefits that come along with biogas systems, the more successful we'll all be. Plus, there's a ton of work underway at the R&D level to help optimize biogas systems and find new ways to utilize them, and most folks don't know much about that either. That's why we're so happy to be a partner on this webinar series and hope that you'll register for all of them. In addition to these webinars, the American Biogas Council also puts on other webinars. If you'd like to know more about them and to receive a notice when we schedule new ones, please go to our website, americanbiogascouncil.org, and click on the big red free biogas news sign up button to share your contact information with us. Of course, we hope you'll also check out becoming a member of the ABC so you can get access to even more market intelligence, insider info on state and federal biogas policy, and contact information for the 200 companies and almost 10,000 individuals in our biogas stakeholder network. Thank you.
Thank you, Caroline. Now, without further ado, I'd like to present today's speakers. Dr. Timothy Ewing will speak about dairy nutrient recovery technologies within an anaerobic digestion biorefinery today. Dr. Ewing holds dual appointments as research engineer at the Center for Sustaining Agriculture and Natural Resources and as instructor and clinical laboratory supervisor at the Jean and Linda Voiland School of Chemical Engineering and Bioengineering at Washington State University. Our webinar today will include a brief overview of the biorefinery concept by Chad Kruger, who is the director of both the Center for Sustaining Agriculture and Natural Resources and the Northwest Washington Research and Extension Center at Washington State University. This will be followed by Dr. Ewing's presentation. I will now hand this over to Chad to get us started. Chad,
all right,
go
thank
ahead.
you. And sorry about the technology problems. We've learned that this is a nationwide technology problem with Citrix, and so they're working on it. If for some reason you have been unable to hear, we are going to record this, and Tara or Sonia, if you could maybe put that in the chat pod so everybody can see that. All right. So thank you for joining this first in our anaerobic digestion webinar series. You can see the full lineup for the series on this slide, including the link to register for future webinars. Today I'll be introducing the overall concept of a dairy manure-based anaerobic digester biorefinery, and then turning the webinar over to Tim Ewing to present in more depth on available nutrient recovery technology options. Future webinars will feature topics including the potential for integration of anaerobic digestion and biochar production by Dr. Manuel Garcia Perez, agronomic evaluation of fertilizer products produced from anaerobic digestion systems and nutrient recovery by Dr. Hal Collins, insights and demonstrations of new economic and emissions modeling decision support tools presented by Drs. Greg Astle and Brian Carlson. Our team has been working from the perspective of implementing manure management technology as an integrated system of technologies that can be assembled to resolve the complex set of manure management challenges, but to do that within a local project context. Each dairy has its own set of management challenges that need to be addressed, and there's no single technology or set of technologies that will solve all challenges for every dairy. The premise behind the system that we're working on is that in some cases a dairy may be able to build a manure management platform based on anaerobic digestion technology that better enables that dairy to address environmental concerns around air, atmospheric, and water quality, while also meeting dairy farm management needs, creating financial opportunity, potential for energy recovery, and then other value-added product development opportunities. In the model depicted in this slide, we present a layout of a possible dairy farm of the future that builds on the traditional dairy of, farm, barns, parlor, cows, and a lagoon and separator system, but then adds to that the anaerobic digestion platform, which enables us to implement co-digestion of food processing wastes, which gives us the ability to address appropriate disposal concerns for food processing wastewater. And then on top of that, the potential to build out other auxiliary technologies beyond the digester that enable us to do more things. So while most digester projects currently produce thermal and electrical energy, the potential exists that we can produce renewable natural gas to be used for vehicle fuel or pipeline quality gas, and actually many other opportunities to use the gas. And then by adding nutrient recovery technologies, as Tim will describe today, we create the opportunity to produce targeted fertilizer products that are familiar to crop agriculture and that have production and processing standards that help us meet quality control for food safety purposes, which is a barrier to using manure in a lot of crop agriculture. One additional idea that we present in this model schematic is the idea that you may be able to have an on-farm greenhouse production system because the excess thermal energy from the anaerobic digestion system as well as the various different fertilizer products are critical inputs for a greenhouse system. And so this anaerobic digestion systems platform is what we have described as the dairy biorefinery. In this slide, we present a schematic of the steps and flows of that dairy biorefinery. And in the process here, we convert raw dairy manure and food waste into value-added products of fuels, electricity, chemicals, with the ultimate goal of recycling and reusing all the different inputs such that the only effluent from the system that isn't reused or otherwise product and sold would be clean air and water. Commercially, we're not quite at that part yet, but what you can see in terms of the red boxes is core anaerobic digestion technology and fiber separation that many hundreds of dairies in the US and many more dairies in Europe and around the world have already implemented. The blue boxes focus on the downstream or add-on products and processes that could be envisioned for implementation in the future. In this slide, we look at the results of a study published by the Innovation Center for U.S. Dairy in 2013 that provides a set of scenarios for low, mid, and high value valuation of this dairy biorefinery if it were implemented on a little over 2,500 dairies in the country. The combination of revenues from tipping fees for co-digestion of food processing wastes, energy recovery for electricity, pipeline gas, or renewable natural gas, recovered value from the various fertilizer products, and then environmental market values for greenhouse gas reduction and renewable energy provide a range from over 1 billion to over almost 5 billion in potential value-added revenue to the U.S. dairy industry. It's important to note that this study is not reporting the profitability of any dairy biorefinery project implemented in this scenario, but it does provide a relative magnitude of the potential opportunity. And in future webinar presentation by Greg Astle, he will discuss the issue of profitability. So while I've talked a lot about the potential of a future biorefinery, I think it's important to note how far the dairy industry has actually come already in implementing the core pieces of this as anaerobic digestion and co-digestion of food processing waste. As I mentioned, there's already hundreds of dairies in the country that have implemented this technology, and many more in Europe and elsewhere around the world. And based on what we've seen already in terms of where the industry has been willing to go, that if we can figure out how to refine the add-on and auxiliary technologies, improve market access and development for products, and make these systems commercially viable and profitable, I think we would anticipate we would see adoption of a number of these systems in the country. So a final slide before I turn the webinar over to Tim depicts a very similar conceptual model, only this time applied in a municipal organics recycling facility. So in this case, rather than a core influent of dairy manure or food processing waste, the idea builds that many of our existing municipal composting facilities around the country already deal with yard waste and food waste, in many cases post-consumer food waste. These existing systems and platforms can be upgraded with the addition of anaerobic digestion systems, slightly different variations of the technology, as well as biochar production and biogas upgrading and various different uses and results from end products. So this concept of a dairy biorefinery is not just limited to dairy, but it can be used in many other livestock operations, as well as the potential to use it in municipal recycling facilities. So now I will turn the presentation over to Tim.
Okay, so I'm just waiting verification that you can see the slide, Sonia.
Yes, we're in good shape. Go ahead, Tim.
Okay, well, thank you very much, Chad and Sonia. I'm happy to be here, and we want to welcome everyone to look at an overview of nutrient recovery technologies related to anaerobic digestion of dairy manure. So we do have some learning objectives for you. We decided to hold off on the quiz at the end, but we're very happy to have you send in your questions at any time during the presentation. And then if you need to contact us or want to go into more detail, we'll have that at the contact information at the end. So the first one is we want you to really understand the biorefinery concept. And I think Chad's given a good overview at the beginning, and we'll talk a little bit more about this along the way. The second learning objective is to just kind of give a picture of what are we talking about today as far as the approaches and the technology for recovering specifically phosphorus and nitrogen, but we'll also touch on just a little bit of the other products and nutrients from this system. And then the third one is really to point out kind of high-level opportunities and challenges that are associated with these approaches or technologies. So I think this is where we can have quite a few questions and have a discussion amongst us on identifying these opportunities and challenges and really trying to get a game plan for moving this whole process forward. Okay, along with the objectives, I do want to point out some constraints or some boundaries that we've placed around this particular presentation. And it's just so we don't get too far afield. We're not going to point out specific vendors, and we're not positioning this presentation to be a technology purchase or investment type document. One of the main focuses is going to be on dairy, and so we're looking specifically right here at technologies related to scraped dairy manure. We do have some others we'll indicate as we go along. And then really we've pulled from a wide range of sources to put this together. So peer-reviewed literature, technical reports, and then various unpublished data, industry projects, personal interviews, and we've noted different areas where we've used those. And then finally, we just want to remind everyone that, you know, when we're looking at extension fact sheets and documents, and this particular presentation, we're looking at economic estimates, and so some of these are made as order of magnitude estimates, and we want to keep that in mind. Okay. So the overview is that we'll look at 4 specific processes within the biorefinery concept. I just want to remind everybody that this is going to be a fairly high-level overview. So if I don't go into enough detail for you, or you have other specific questions, then please do use that question pod or send in an email to us at the end. And then as Chad touched on, you know, the biorefinery concept can include a really large number of variations across a number of facilities. And so here we're just going to focus on a particular configuration and then at the end we'll touch on kind of an expanded view as well. So the first unit that we'll look at is primary solid separation. So I should take a step back real quick and say that in the diagram we're looking at the dairy, we have our cows, and then everything starts in this case with our anaerobic digester, with our main product being the biogas. And then the first unit that we'll talk about here is primary solid separation, which will be a fiber product that we're looking at. The second unit is what we'll term advanced solid separation, and this is really focused on a phosphorus product at this point. We are then going to branch, and we're going to take a look at what we're terming nutrient recovery, and these are different technologies related to getting nitrogen and phosphorus out of the system. And then the other branch point we'll look at is water treatment. What can we do to get clean water out? And it's important that this diagram shows both the sequential nature and that there is a branched path. And the main reason here is that some of these units that are downstream depend heavily on the prior treatment steps. And so especially, we'll just point out real quick, the water treatment. If we're talking about filtering or reverse osmosis or some of the things we're going to look at, if we haven't gotten the fiber out of the effluent coming from the digester, we have a lot of challenges that we're adding to getting the water treatment portion. Okay, so each slide that we look at is going to be set up fairly similar to give you an orientation. We've got some visuals that we'll talk about. We've got some bullet points, and then we'll look briefly at some of the economics or performance of the process. And so really, the primary solid separation, the technology is mature and it's in widespread use. This is one area that we can really focus the industry on getting dairies primary solid separation products, getting the equipment in, and having them utilize the products from that. And so, you know, the main focus here is to get a stackable pile of separated fiber. And this fiber then can be used, as it's shown in panel B, for on-dairy bedding. It can also then have the option of being converted into a value-added soil amendment. And so market, there's peat moss, there's other soil amendments that replacements and soil amendments that are being shown. And so if we just look briefly here at the recovery performance, we're talking 10 to 20% total nitrogen, 10 to 20% total phosphorus. And then I'm not going to go heavily into the economics here, but we can look at the operation and maintenance, the O&M costs, and the revenue, the last line. And we can see that we're at least on the positive side for primary solid separation. So again, a mature technology, it's in widespread use. This is ready to go into being pushed out into more dairies across the country and internationally. Okay, so the second unit that we'll talk about is the advanced solid separation. This is a mature technology, but it's fairly new to be used on the dairy. So we're talking about things like centrifuges, belt presses, dissolved air flotation equipment. So we've seen this now in municipal systems. We've seen it in industrial wastewater treatment. and now we're seeing it start to come onto the dairy as this advanced solid separation. And really, where these types of products are making an impact is in the total suspended solids. And so it's taking a lot of the phosphorus out of the effluent. And so this unit is really focused on phosphorus production. The challenges here are really about the equipment, about the, trying to find efficiencies where possible, and then related to what do we want that final phosphorus product to look like. Because, do we need it to be a dry powder? Do we need to have it as a partial? Can we mix it with other biofertilizers? And so the challenges are related to both managing the operating and maintenance as well as managing the final products. And then in panel B, this is really the first step where we have a water product that has some potential to be reused on the dairy. So, it still looks colored at this point, which it is. It still has nitrogen in it, but this is really the first step where we can start thinking about what we can do with that water product. Now, as far as recovery performance here, 30 to 35% on the total nitrogen. Again, this is mostly focused on the phosphorus, 70 to 90%. And here we're still looking on the positive side for operation and maintenance versus revenue. And so this again is a mature area of technology, but it's really now focused on how can we push this out into the dairy industry. Okay, so we'll move on to the third unit, and we have 5 different systems that we'll take a look at for nutrient recovery. We'll look at Struvite, Nitrification Denitrification process, ammonia stripping, algae, and vermiculture. And so, as an engineer, we get really excited about the engineering challenges. And so the first 3 are really kind of engineering. We're going to think about how we can advance these efficiencies, get them out there and working. And the last 2, as we'll see, are still we have some research and development to do, but certainly with vermiculture, it's popping up more and more now, and so we'll look at that as well. Okay, so Struvite Crystallization. Again, this is one of those mature technologies from municipal wastewater. It's really a very high quality, market-ready product, and it has characteristics with nitrogen, phosphorus, and some other nutrients and components like magnesium that make it attractive for multiple uses. But really, this is very dependent on unit 1 and 2. And especially with any of the total suspended solids that have both magnesium and calcium, can partially disrupt this, can make it more challenging to get a good Struvite efficiency and crystallization process. And so while again this is mature and it's in commercial use on a dairy of around 1,000 cows, it still needs some work for efficiency. And so again, focus mostly on total phosphorus. So we're at about the 10% total nitrogen and 70–80% total phosphorus. And now this is where we need to really focus on efficiencies and how we can improve the process, because the O&M costs versus revenue are not quite there yet. Okay, so the next one we'll look at is nitrification and denitrification. This process, again, is fairly mature for municipal facilities, but there's questions about implementing it on the dairy. At this point, as the panel photo there shows, this is an overview of a swine facility. this brings up a question about, how the different manures contribute to the different biorefinery concepts, and we might get into that a little later. But the difficulty here in the nitrification denitrification technology is that we're going for a product which is essentially atmospheric nitrogen. And so how do we incorporate that into the biorefinery concept as a value-added product? The challenges here are really related to the form of the nitrogen in the dairy effluent stream, which is primarily in the ammonia form. And so this nitrification denitrification process on the dairy effluent actually is much longer retention times than a municipal facility. It could have more consumables that need to be added to adjust the effluent. And then at the end, we're essentially blowing nitrogen off into the atmosphere. Although in a much better form than ammonia, the question is there something else we could do with that nitrogen? The other part of the challenge is the very last bullet point there, being that this is really one of the reasons there's a branch between nutrient recovery and clean water, because there can be some challenges related to moving beyond this step and trying to get treated water out of the system. So here we're looking at mostly a nitrogen. There is some total phosphorus recovery as well. It does have a fairly low operating and maintenance cost per cow year, but again, the revenue is either a question or not applicable for the nitrogen removal. Okay, so we'll look at ammonia stripping next. This one I'm just terming developing as a technology. We see that the equipment and the process is now well known, and we're starting to see it pushed out to more demonstration sites and being built out at a commercial scale. But essentially we're looking at here contact towers, and generally there's an aeration step, there's an acid wash step in a contact tower, and then we're producing a liquid, or it can go to a crystallizer to become a solid ammonium sulfate product. Really here, some of the opportunities are related to, there's not a lot of outside consumables that needed to be added to the process. So the carbon dioxide that's in the biogas can be used to pump back through the effluent. We can do some aeration. There can be some other couplings with some other demonstration of exchange membranes to improve the process. So there is quite a bit of opportunity here for system improvement, and the biggest challenge is about the cost. So here again, we're looking primarily at total nitrogen, and there's not much in the way of total phosphorus recovery. And again, our operation and maintenance costs aren't too far away from our revenue, but we're just not quite there yet of showing the positive side of that. So again, this is an area that's developing, it's being pushed out there into the industry, and we're looking for efficiency improvements and coupling in order to improve the overall revenue streams. So algae systems, algae definitely comes and goes as far as a subject matter in research institutions. So we'll term this one under active research, and there's a variety of ways that we can approach algae systems. We can do open raceways, which are essentially ponds or canals where we run the solid separated effluent, and we have seed reactors that we can use to grow up cultures of algae and then release them into these raceways to grow on the effluent. There's other research undergoing that looks at internal systems, so photobioreactors, where we concentrate the algae and we have artificial light systems to allow them to continue to do their photosynthesis and grow. That's kind of open raceways in panel A there, and then panel B is showing a dried algae biomass. So this system, at this point, the focus is really on wastewater treatment or the effluent treatment. So we can go ahead and put the algae in there, we can grow it, we can harvest it, but the challenge then is, where do we go with that? Is there an opportunity that this could be used as animal feed? Could it be used as a biomass for raw input into another process? A lot of people want to see this used as a biofuel feedstock. So lots of potential opportunities there, but again, this is more under active research. And we can see that growing algae on the effluent shows 50 to 80% both total nitrogen and total phosphorus recovery. But this is, our challenge is, how do we improve the efficiency? How do we improve the yield? How do we find a market that's really going to drive the revenue and drive the O&M costs down? Okay, this is a fairly new one for me, the vermiculture, and I've heard quite a bit about it the last few days. So this is one that I'm going to kind of split and say under active research, but also it's being pushed out and it's on dairies now. So essentially this is, if we want to say, it's a tank filled with worms. And so we're looking at using that biological system to filter the dairy effluent. So this is, we could say, passive aerobic bioreactors. It is a layered approach, so there's layers of both the organisms themselves as well as castings, which are the shells of the organism. They can have bulking agents that would be familiar to any aerobic bioreactor. And so the idea there is to filter the effluent, allow the organisms, the worms, to biologically treat, and then that effluent that comes out of that system then is can be used for other downstream processes, including water treatment. So there's some potential here for both selling live worms as well as the castings. So we could see that pretty heavily tilted towards nitrogen recovery, 70 to 90% total nitrogen. We do have a component here of total phosphorus, and this is very interesting in that our operation and maintenance costs and our revenue, and especially the potential revenue once markets can be developed, are not too far away. So this is one that should be on everybody's radar to take a look at and see where it's going. Okay, so we're going to branch here and take a look at the water treatment unit. And again, kind of the lower right corner there, we're really dependent now on going from AD through our primary solid separation, our advanced solid separation, to get to the point where we can look at using membranes or potentially evaporation as a water treatment unit. So again, we've seen this on a few of the other units. It's a very mature technology, but again, it's relatively new on the dairy. The equipment, because the technology is mature, is known, especially to municipal and industrial wastewater treatment. So microfiltration, reverse osmosis, various different size screens, plates, membranes. And it's made to produce water that's ready for some other use. And we can look at this in more detail offline, but we really want to set the target is what we would look for. So typical performance, 50 to 60% clean water, and then the remainder of that would still be considered for other water uses. Biggest challenges here again is it's highly dependent on the upstream processes, and so solids control, and then really setting the system to our particular application. So as we've seen, both municipal industry and now on the dairy, very high total nitrogen removal. Essentially 100% of the total phosphorus is removed. And this is another one where it's the O&M costs to revenue are promising. And so efficiencies, tailoring it to a specific application, we need to look at how this can be improved for on dairy and the biorefinery concept. Okay, then the last unit here, before we kind of summarize, we'll look at evaporation. I'd again kind of put this one under active research developing, in that there's work to be done, but there is a system that's been published that's out there. Really the opportunity here is related to heat, and so how much available heat do we have that could drive this process? So if we're in a geographic area, or if we're co-located with another industry and we can find the heat to drive the system, then it could be beneficial to us. Again, the challenges here are related to the upstream processes. We need to get solids out, and then we need to focus on what the product is that we're looking for. So this particular technology is tipped a little more towards total phosphorus removal, but we do get about 40% total nitrogen. And then we have challenges related to finding efficiencies, driving the O&M costs down, potentially finding other revenue sources for the products. Okay, so that gives us, again, that high-level overview of those 4 units. And so I wanted to, this is a really busy slide, but I wanted to try to put everything in front of you at the end. Please note that there were some subscripts on the parent slides underneath these tables. And so if you see something here, go ahead and go back when you get the slides and take a look at what the subscripts and the notes are. But in the top left panel here, we have the primary solids and the advanced solid separation. Pardon me, and we can see that the O&M costs and the revenue are there. They're there now for pushing this technology, this approach out to the dairies. The bottom panel, I'll jump to that since that was the order we looked at. The various nutrient recovery technologies and approaches. Again, they're all red, meaning that we're not quite there in the O&M versus revenue, but we can point out that at least with Struvite and with Vermiculture, and even sorry, I missed the ammonia stripping, we're getting close there. So Struvite, ammonia stripping, Vermiculture, we're certainly in the ballpark, and we need to really look at what we can do to push those ones forward. Again, there's questions about what we want to do with nitrification, denitrification on the dairy. And then as far as algae goes, we just need to keep working, keep up the research, look at different systems and what we can do. And then again, for water treatment, we're still, I've highlighted those red to show that we're not quite there yet. Although membranes can be in that kind of pink area where it's close. And so we need to look at efficiencies there, technology improvements, as well as tailored to the application that we're focused on. Okay, so again, this kind of connects back to what Chad was showing at the beginning. is that we have the future biorefinery concept, in that we can look at lots of different units to plug in here. So start with the off-dairy organics, mix it into the co-digestion of anaerobic digester, get our biogas, look at upgrading that, look at utilizing it for other feedstocks, and again then we go into solid separation, nutrient recovery. One that we're looking at here at WSU is the pyrolysis process. So again, we can bring off-dairy woody biomass in, combine that with the fiber, produce biochar, produce usable heat for other processes, and then we can strive for some applications on the water treatment, such as animal drinking water, and then going out into the remaining for fertigation or for field use. Okay, so to kind of start winding down here and move towards the question session, I want to point out that we have an extension fact sheet that's in preparation. This presentation drew heavily on that first sheet there, so applications, approaches to nutrient recovery. We also would point out that there's some other publications here, nutrient recovery by biogas digestate processing, there's a review of emerging technologies, and also some manure processing activities. So we have a mix here of additional references we think would be of interest to you from both the US and from Europe. Certainly like to acknowledge USDA and NIFA and the Water Research, Environment Research Foundation and EPA, American Biogas Council. Here at Washington State University, we have the ARC, we have CSANR, we have the Department of Biological Systems Engineering, point out Nutrients LLC, Dairy Management, and then just all of the agencies, personnel, people that we've talked to for interviews and valuable information. There is an endless list there that are very beneficial to us. And this is our landing page so that you have an opportunity to have our contact information there for Chad, Georgine, myself, our emails. And so I think we're open for questions.
Thank you, Timothy. Yes, we do have time for just a couple of questions. Unfortunately, that's shorter than we had planned given the technical difficulties, but we'll jump right in. First question, do you think that co-digestion with 2 or 3 substrates could be the solution to improve digestate quality in terms of nutrients?
I think that's a great question, and there is quite a bit of research going on in co-digestion and how that can ultimately affect the effluent, and then how we might be able to target nutrient recovery technologies to that particular effluent. Kind of a corollary, or I'm not sure the word to use, but there's similar work being done in targeted composting at this point, to where certain co-products in the composting pile are being used to tailor nutrients to a specific product. So I think that's a good question, and I think that there is research out there that is going in that direction to help us improve both recovery of nutrients from the co-digested products, as well as tailoring specific applications and products out of that.
Thank you, Tim. Another question that came in. Scrape manure systems obviously reduce the water content of the digester feedstock. If dairies use water spray removal of manure, will this significantly increase the system's cost of anaerobic digestion for their farm?
This is a good question as well. There is quite a bit of literature, and I may put that off to having you email, but there are technologies now that are tailored to anaerobic digestion of scrape systems of flush systems, as well as concentrated animal feedlot type manure. And so it doesn't necessarily have to impact the cost maybe in the way you're thinking. Yeah. Is that certain scrape systems do use a kind of a sorry, I'm losing the word, where it concentrates the manure before going into the digester, which then frees up some of that liquid to be returned to a storage lagoon, which can be used for flush system later on. There's a lot of possibilities here for using manures of all types to go into the digestion process. Do you have anything to add on that, Chad?
Yeah, I'll add just a little bit. I think what you just stated about it's not nearly as significant of a financial barrier to flush systems as it's been assumed to be, that it can be done with relatively low technology approaches like you described, just settling and concentrating. So it hasn't been a barrier to those dairies that have been flush and wanted to move toward a digester.
Thank you, Timothy and Chad. We have time for one or two final questions. The next one is, how is the revenue derived, i.e. on the RO technology? Are you selling a fertilizer or water product?
That's a great question as well. So at this point, that revenue, there's an asterisk under the table. We can provide some follow-up information, but that's really focused on the components, the bio-fertilizer components that would come out of that process. And so that's one I probably should have highlighted about tailoring. Do we want water, clean water? Is that our product? And how can we assess, put a value on it, versus just focused on the revenue from the biofertilizer component? So
I'll add a little to this one too, kind of generally not even specific to the RO technology, but for all of these products, the question of market and valuation is a challenging question, and in some cases it's because it's a product that's not currently utilized within, say, cropland agriculture. In other cases it is a product that already does have a market, and the question is much more of an engineering question. But the challenge of valuing these products in terms of when you do the study is you look at those markets and try and assign a price based on what's happening in the market at that time, or what's happened in the market over the prior few years. And if that product that you're producing is one that's commercially available, there's a lot of volatility in those prices for fertilizer nutrients already. If it's a product that is similar to another product, then you have to make some strategic decisions around how you assess the similarity of the product you're producing relative to something that does have a value in the marketplace. And so I think this is a challenge that, you know, moving forward is a priority area for research and development to figure more of this out.
Thank you both. I'm going to go with one more question before we wrap up. How is manure being treated beyond primary solid separation to prepare it for the RO treatment?
I think you have to show that there's some secondary or advanced solid separation, and so it's either centrifuge, dissolved air flotation, belt presses. There's going to be a sequence of additional solid separation steps that need to occur before you get to the point you're ready to go into a reverse osmosis or other filtering technology.
Right.
Thank you very much, Tim.
One more thing in response to all of these is the questions around product quality and integration of biochar and all of these technologies. As we mentioned early on, several additional installments in this webinar series will build on what we've discussed today and give more input on that.
Thank you. So thank you to both our speakers today. I'm sorry we did not have time to cover all the questions, but feel free to reach out to Chad or Timothy or Georgine on these topics. As you sign off, please take a minute to fill in the evaluation survey that will pop up for you. We really appreciate the feedback. And then our next webinar is scheduled for February 24th at 1 p.m. Eastern and 10 a.m. Pacific time. Dr. Manuel Garcia Perez will be discussing the potential for biochar production and utilization within an anaerobic digestion biorefinery. And so hopefully some of those questions that came in related to biochar can be answered then. So please register to join us again on February 24th. And thank you for your patience with the issues we've had with this webinar. We look forward to seeing you again on the next one.